Section 2.8 is all about the normal curve. In this section, we're going to do several things. First, we're going to look at the properties of a normal distribution. We'll calculate a z-score and use it to find the area under the normal curve. And then we'll take that area and calculate it into a percentage of the data that lies between these values. Let's first look at the different types of distributions that we can have. The first type of distribution you can have is what's called a rectangular distribution. When you're talking about a rectangular distribution, in general, you're looking at the shape of the distribution, and notice it looks like a rectangle. An example of something that could be a rectangular distribution would be like throwing a dice or a die. You would anticipate the probability of rolling a 1 versus a 4 versus a 6 would all be the same. And when that happens and all the frequencies are the same, you form a rectangle. You can also get a J-shaped distribution, meaning it is either always increasing or always decreasing. Sometimes you have what's called a bimodal distribution, and when you look at a bimodal, it seems that two sets of data keep coming up over and over and over again, and notice you get two bumps in the graph. That's considered bimodal. Sometimes we consider the data to be scaled, and when we talk about something being scaled, we look at the location of where the tail is. So if I was to draw a little graph on the one that's scaled to the right, notice that the tail seems to be on the right-hand side. So wherever the tail is located is where you say the skewness is. So if the tail's on the right, you're skewed to the right. If the tail's on the left, you're skewed to the left. Usually we don't look at histograms, instead we draw smooth curves, and these smooth curves can be considered the same way. With the tails on the right, then you're skewed to the right. If the tail's on the left, then you're skewed to the left. When you look at skewed distribution, there's a specific relationship that happens between the mean, the median, and the mode. Keep in mind that when you have lots of data points that are on the right-hand side, it's going to affect your mean, and it's going to pull the mean to the right. The mode is going to be where the bump is. That's the most common answer that you see, and then your median is going to end up being between those two values. So same thing, if you are skewed to the left, that's going to pull your median towards the left. The mode is still going to be the highest point on the graph, and the median is always going to be between the mean and the mode. We're going to focus most of our attention on the normal distribution. There's several things that follow the normal distribution, such as IQ scores, heights and weights of people, lengths of a boa constrictor, the wear out mileage of automobile brakes, etc. And in general, when you look at a normal curve, you're going to have the bump right in the middle of the distribution. So when you look at a normal distribution, we're going to call that distribution a normal curve. The normal curve should always be bell-shaped, and it should always be symmetric about the mean. The mean, the median, and the mode should all have the same value, and they should all be dead center. So when you look at that bell-shaped curve, the mean, the median, and the mode are all going to be directly in the middle. There is a rule called the empirical rule. The empirical rule says that if you draw your normal curve and you put your mean in the middle, if you go one standard deviation to the left and one standard deviation to the right, 68% of the data should land in those first standard deviations. If you go 2 standard deviations to the left and 2 standard deviations to the right, 95% of the data will lie in that zone. And if you go 3 standard deviations to the left and 3 standard deviations to the right, 99.7% of that data will lie in that zone. The extra guys are kind of your outliers. These are your oddballs that are out here at the very, very, very ends. In order to calculate how far away we are from the average, we calculate what's called a z-score. The z-score is going to tell you how far in terms of standard deviations you are from the middle, which is the average. The formula to calculate a z-score, you need to take the value of your piece of data, which we usually call x. You need to subtract it from the mean, which we call x bar. And you need to divide it by the standard deviation, which we usually call lowercase s. So let's look at a couple examples of just calculating z-scores. So I want you to find the z-scores for the following pieces of information. You need to know that this is normally distributed. If something is not normally distributed, the z-score does not apply. It has a mean of 60 and a standard deviation of 15. So let's look at our first value of 75. So in order to calculate our z-score, we would take 75 minus 60 and divide that by 15. Well, 75 minus 60 is 15, and 15 divided by 15 is 1. So the value of 75 is 1 standard deviation away from the mean. So if you wanted to see a visual of what that means, your mean is dead center at 60. If you go 1 standard deviation to the right, which is 15 units away, you will have your value of 75. Let's look at another one. Let's look at the 81. Our value is 81, our mean is 60, and our standard deviation is 15. So if you do the subtraction, you'll have a 21 over 15. You always want to turn these into a decimal, so that would be 1.4. So if you look at your average, here's 1 standard deviation and here's 2 standard deviations. We're 1.4 standard deviations away from the mean when we're at 81. You could do the same thing with 60, but you should notice 60 is a number that you've already used. Your data point is 60, your mean is 60. So that means you are going to be 0 standard deviations away from the mean, which means you're on the mean. The 33 is going to put you below the mean. My data point is 33. My mean is 60. My standard deviation is 15. That's going to give me a negative 27 over 15, which is negative 1.8. All it means that you're negative is that you are below the average. So you're down here somewhere near negative 1.8 standard deviations away. Sometimes they're going to ask you to calculate the percent of the data that lands between two data points. So there's a procedure to do this. The first thing you want to do is you want to draw a diagram of the normal curve. You want your average to be dead center. Then you need to indicate what you are looking for. So usually they'll tell you they want you to be between two values. And the way we indicate that is by shading the region that's between those two values. You're going to use the formula to convert each of those values into z-scores. And then you'll write those z-scores on the diagram. You're going to then use a table that's provided in your textbook, and you're going to look up the z-scores on the table. Now there's two tables, so it depends on what type of z-score you're working with. If you're looking for an area that is going to be to the left of something, and you have a negative z-value, you're going to use table 12.8a. If your z-score is positive, you're going to use table 12.8b. If you're looking for area that's to the right of a z-score, then you're going to look your z-score up on the table, and you're going to have to do 1 minus the area that you found from your table, and that's going to tell you how much area is to the right of your z-score. So notice the table only gives you the area to the left. If you are trying to find, if you're trying to find area to the right, you can also use symmetry. You can find the area that's to the left, and then you can flip it. I usually do the subtraction technique. If you're trying to find the area that's between 2 points, you first need to find the area of the bigger z-score. Then you need to find the area of the smaller z-score, and then you'll subtract the two. You'll take the big minus the small, and that will give you the area that's between them. Last, you want to change all the areas that you found into percents, and to change an area into a percent, you just multiply it by 100. Let's look at an example of this, and I will show you how to calculate the areas using the table. I will also show you how to calculate the areas on your calculator because your calculator can do all of this stuff. I find most students just prefer to do it on their calculator, but let's see. Okay. Assume that the length of time for a horseback ride on the trail at Triple R Ranch is normally distributed with a mean of 3.2 hours and a standard deviation of 0.4 hours. What percent of horseback rides last 3.2 hours? Okay, so first thing we want to do is draw our normal curve. We know that our mean is dead center at 3.2. And we want to know what percent of horseback rides last at least 3.2. So they're wanting to know what the chances are that you are 3.2 or bigger than 3.2. Well, this one you can just do mentally if you want to, because 3.2 is your mean. They are asking you to be larger than 3.2, which is everything to the right of the mean. And if you use what you remember from the previous problem, from our notes, we know that if you're on the right-hand side, that's 50% of the data. You don't even have to do a calculation here if you don't want to. You know 50% of the data lands on the right-hand side. And keep in mind, you have to take this and multiply it by 100 to turn it into a percent. No calculation needed here if you remember all your information. So 50% of the horseback rides will be at least 3.2. Now we need to remember our mean was 3.2 and our standard deviation was 0.4. What percent of horseback rides last less than 2.8 hours? So let's draw our normal curve. Remember that 3.2 is our mean. We are wanting them to be less than 2.8. So 2.8 is going to be down here. We're wanting to be less than 2.8. So that's this tail over here. So essentially what they're asking you is how much area is in that left tail. Okay, so first thing you have to do, if you're going to do this by hand, is you have to calculate your z-score. So we need to take our data point, which is the 2.8. We need to subtract our mean, which is the 3.2. And we need to divide it by our standard deviation, which is 0.4. Okay, well 2.8 minus 3.2 is negative 0.4. Negative 0.4 divided by positive 0.4 is negative 1.00. Now we need to go to our table of values. Okay, so I'm going to take a video for you so you can see how I'm getting these values. Okay, so I have a z value of negative 1.00. So when I'm looking at this table, I need to go to the z column and I need to find the negative 1.0, which is here. And then I need the second decimal place because it was 0.00. So notice the 0.00 column right here. I'm going to scroll all the way down. And notice I have it circled here for you. I have a 0.1587. Okay, so that means the area under that curve is 0.1587. And then keep in mind that you are wanting to turn it into a percent. So you multiply by 100, which is going to turn you into 15.87%. So 15.87% of horseback rides last less than 2.8 hours. Now, how can I do this on my calculator? Because I know that's what you really want to know. So let me show you how to do that. I'm going to clear what I did from last video. Okay, so first thing I'm going to do, see this button that says VARs? You need to get to the DISTR for distribution. So we're going to have to hit second VARs, okay? Now, there's a couple options here. There's normal PDF and there's normal CDF. Remember, you're looking for a cumulative distribution. So we're going to select option 2, which is normal CDF. Now, it's going to ask you for your lower bound. So what does that mean? Well, if you look at your data was going left forever. So your lower bound needs to be a really large negative number. They're using scientific notation here. This is -1 times 10 to the 99th power. You can keep it like that, or if you prefer, you could put like -10,000 in there if it makes more sense to you. We're just going extremely far left. Then it wants to know my upper bound. Your upper bound is where you wanted to stop your shaded region. We wanted to stop at 2.8. Then it wants to know your average. Your average in this problem was 3.2. And then it wants to know your sigma. Your sigma in this problem was 0.4. You can hit paste and enter. And notice it's going to tell you 0.15865. So if I rounded that, I would get my 0.1587. Okay, let's try another one. What percent of horseback rides are at least 3.7 hours? Okay, so I always start with drawing my diagram. My mean was 3.2. I want my horseback ride to be at least 3.7. So remember, at least means you can be 3.7 or larger than 3.7. Okay, so you would shade all of this region in right here. Okay, now if I'm doing this by hand, I'm going to calculate my z-score. So I'm going to take the value I want, which is 3.7, minus my mean, which is 3.2, divided by my standard deviation of 0.4. So that would give you a 0.5 over a 0.4, which is 1.25. Now, keep in mind we're going for the area to the right. Okay, so when I look up 1.25, it's going to tell me the area that's on the left. So I'm going to have to take 1 minus whatever number they tell me in the table, and that's going to tell me how much area is on the right. Okay, so let's look at our table and calculate how much area is to the left of 3.7. So I'm going to have to use the second sheet of my table since I have a positive value. So I am looking for my z value, which I said was 1.25. So I'm on the positive part, which is part B, and I'm scrolling down. I've got a 1.1 and a 1.2. Now I need to work my way over to 1.25. So this is 1.20, 1.21, 1.22, 1.23, 1.24, 1.25. So I'm getting 0.8944. So I'm going to take that value, because remember that's my black region, and I'm going to do 1 minus that. 0.8944. Well, 1 minus 0.8944 is going to give me 0.1056. And then I will turn that into a percent by multiplying by 100, which gives me 10.56%. So in terms of this problem, only 10.56% of horseback rides are 3.7 hours or longer. Now, let's do this in my calculator, because again, that seems to be your preferred method. Okay, so in my calculator, I'm going to go back to second VARS. I'm going to select option 2 for normal CDF. Now, I need to know my lower boundary. So if I look at my picture, this time my lower boundary is the 3.7. My upper boundary is infinitely high because I keep going and going and going. So I'm going to put my lower boundary as 3.7. And I'm going to put my upper boundary as just a really high positive number. I usually go with like 10,000. My mean is still 3.2. My standard deviation is still 0.4. And then I'm going to hit paste and enter. And notice it gives me 0.1056. So, same answer I got by doing it by hand. You take that 0.1056, times it by 100, and you're done. Okay, let's look at one more situation. This one, I want to know what percent of horseback rides are between 2.8 hours and 4 hours. So let's draw our normal curve. My average is right in the middle at 3.2. And I want to be between 2.8 and 4.0. So I am looking for the region in the middle. So I just like to shade it. Okay? Now here's what you got to do. You're going to have to find a z-value for each situation. So I like to find the upper one first. So the z-value of the upper number is going to be 4 minus 3.2 divided by 0.4, which is going to give you a value of 2. Then I'm going to find the z-value of the bottom one next, the left one next. So I'm going to do 2.8 minus 3.2 divided by 0.4, which is going to give you a value of -1. Then we're going to look for the area to the right of each one of these. And we're going to do that using the table. Okay, so I'm going to go to my table. Let's take a little video here. Okay, so let's do the 2 first. I've got a 2.00, so I need to scroll down to 2.00. So that is going to be 0.9772. Okay, so the area to the left of 4 is 0.9772. Then I need to find the area to the left of 2.8. So I'm going to use the first page of the table. And I need to find my -1.00. So I'm going to scroll down. -1.00 is that 0.1587. Okay, 0.1587. Then I need to subtract the 0.9772 minus 0.1587, and I'm going to get 0.8185. And then I have to turn it into a percent. I'm going to do that by multiplying by 100. And when I multiply by 100, I'm going to get 81.85% of horseback rides last between 2.8 and 4.0 hours. Now, if I was doing this on my calculator, I'm going to go back to second vars. I'm going to select normal CDF. My lower limit this time is just 2.8. My upper limit is 4.0. My mean is still 3.2. My standard deviation is still 0.4. And I'm going to paste and hit enter. And notice I get the same answer, 0.81859. Now, if you rounded to 4 decimal places there, you'd have 0.8186. So just keep that in mind when you're in My Math Lab. There may be a slight rounding issue. Usually My Math Lab is fine with a little bit of rounding, but if you're having issues with the rounding from your calculator, go back and use the table. Last problem, and then we're going to call this a day. In a random sample of 500 horseback rides at Triple R Ranch, how many are at least 3.7. Now, keep in mind that we have already completed part of this problem. If you looked at question C, we already found out how many were at least 3.7. From question C, we found out that 10.56% of all horseback rides are at least 3.7. So what you can do is convert that back into a decimal. And then what we're wanting to know is if we looked at 500 horseback rides, how many would have lasted 3.7 hours or longer? So you just need to take the 0.1056 and multiply it by 500, and you'll get a decimal, 52.8. So approximately 53 out of 500 horseback rides are going to be 3.7 hours or longer. All right, let me know if you have questions.